All right, so let's go into exactly what we mean by Gaussian elimination. Specifically, what are the three things you're allowed to do in Gaussian elimination, and also talk about why it works. What this says is that if one system of linear equations is transformed into another system using one of these three operations, then the two systems are equivalent. And remember, what equivalent means is that the two systems have the same solution set. Meaning, if one ordered list of numbers is a solution of one, it's got to be a solution of the other one as well. Oh, by the way, a little side note here. Gaussian elimination was not actually invented by Gauss. It's actually been known for a long time. The first written record comes from China over 2,000 years ago, and it was independently invented in several other cultures just because it's a thing that comes up a lot when you're dealing with numbers. Like a lot of the time, there's more than one unknown number you have to figure out. Like there's all kinds of basic applications you did in like your algebra 1, algebra 2 classes in high school. So, yeah, people needed to figure those things out and they did over the millennia. But I guess Gauss did a lot of big things with this elimination method. Maybe he streamlined it and expanded it a little bit, or some of the things we learn in linear algebra that we'll do later were figured out by Gauss. So, calling this Gaussian elimination is kind of like how basketball, the sport, is named after Carl Basket, who's the greatest basketball player that ever lived. So, anyways, let's see what the operations are and talk about why they don't actually change the solution sets of the systems. So, first we have swapping, which is just like writing the equations in a different order, switching the position of two equations. So, let's look at an example. So, if this is a system called S, let's just give the whole system a name like S, and it has these two equations written in this order, then we could do a swapping operation. And my way of writing that is just saying equation 1 and equation 2 are getting switched, and that will lead to the following system. And this system, I mean, technically, it is the same equations, but they're written in a different order, so there is something different about them. So we'll give it a different name T. But clearly, if you have an ordered pair that is a solution of one system, it makes this equation true and this equation true, then of course it's also going to make this equation true and this equation true, and vice versa. So they're definitely equivalent. Let's look at scaling next with an example. An example of a scaling operation might be multiplying both sides of equation 1 by 7 or something. And that will give us a system that looks like this. And you can clearly see that these are going to be equivalent systems, just like whatever ordered pair you plug in that makes both of these true is also going to make both of these true. The second equation didn't change, so its solution set's definitely not going to change. And the first equation has two equivalent versions. And you've studied in algebra why what those are equivalent. It is important to know, though, that we cannot multiply it by 0. That will change the solution set. Let's see why. Multiplying the first equation by 0 on both sides gives you 0 equals 0 here. And any value of x1 and x2 will make that true. 0 is always equal to 0 no matter what. So this system together with the second equation now has an infinite number of solutions, because any solution of just the second equation is also a solution of the whole system. So it's not equivalent to S. So don't do that. All right, let's look at the more complicated one now, multata placement. Multata placement says you can replace each side of one equation by the sum, that's the add part, of itself and a multiple of another equation's sides. And in most linear algebra textbooks, this is called simply replacement, but I don't like that terminology because it doesn't really tell you what it does. People get that mixed up with swapping or interchange. So what you're really doing is you're taking a multiple of both sides of one equation, adding it to the other sides to replace, adding it to the other sides of a second equation to replace that second equation. So let's see why this works. And we'll go into a bit of a proof here in some detail. And I know you might not have had much training in writing proofs in other classes. That's okay. We are going to learn how to write proofs in this class. So this is just going to be a quick little preview of how to do that. If you don't know how to write this proof yourself yet, that's okay. But hopefully the reasoning makes sense. What we want to show is that the two systems are equivalent when you do a multata placement operation. So maybe the system S is like the same system we've been looking at here. So we could just use that as an example. But to do a real proof, not just a proof by example, which isn't a real proof, we want to write out what this might look like in general. Like any system of equations where you do a multata placement operation might look like the following. The system S here has equation 1, which has left side, which we write as L1, and the right side is R1, and L2 is the left side of equation 2, and R2 is the right side of equation 2. And maybe there's more equations in it. That's what the dot 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 means, but just to simplify it, let's just say that the one we're replacing is equation 2. And the way to write that using this sort of notation that I like to do is we're going to do k times equation 1 plus equation 2. That's the multiplication, the addition, and then we're replacing equation 2 with that result. And so the result will look something like this. Leaving equation 1 alone, but the one that's getting replaced is equation 2. And let's call this new system T. Like so. Okay. What we want to show is that any solution of system S is also a solution of system T and vice versa. So here's how you would write out like the starting point for a proof where we're showing that these two solution sets are equal. So first, we need to show that any solution of S is also a solution of T. So you write suppose or assume that you have some solution of system S here, and the goal is you want to show it's a solution of T as well. So that's why I write want to show, WTS, want to show it's a solution of T as well, just to lay out what is the goal for this part of the proof. But we also have to prove the converse of that, that if you have a solution of T, then it's also going to be a solution of S. So to write out the beginning of that part of the proof, it would look the same idea, just with the t and s switched. So this is laying out the two things that we have to do for this proof. Let's look at the first one first. We're assuming that we have a solution of S. What that means is that plugging that list of numbers into wherever the variables x1 through xc show up here is going to make it so the numbers that you get on each sides of the equations are equal. Just writing this out here, we're saying that plugging in this list of numbers into the variables is going to result in some number for L1 and some number for R1, and they're going to be the same number. And same thing with L2 and R2. So when I say like L2 equals R2, I don't mean an equation with variables in it anymore. I mean L2 is now a number because we plugged values in for all the variables, and R2 is now a number and they are the same number. This means that K times L1 is the same number as K times R2. And since L2 and R2 are the same number, it means that L2 plus K L1 is the same number as R2 plus K R1, meaning we just added the same number, KL1 and KR1, to both sides of an equation that had likewise the same number that were already equal. So those are definitely the same number now. And that means now that S1 through SC makes this equation true, which is the only difference between S and T. So the solution S1 through SC of S is now also a solution of T. It makes all of the equations true. Now let's look at the second part. We're assuming that we have a solution of T. We want to show it's also a solution of S. And again, what it means for this to be a solution of T is it means plugging it in for the variables everywhere, and simplifying is going to result in each equation being true, as in like the same number on each side of each equation. So that means the number L1 is going to equal the number R1, and the number L2 plus KL1 is going to be equal to the number R2 plus KR1. And the fact that we have a solution of T means it's specifically a solution of the first part of T, and if you multiply both sides of that by the same number K, then those two numbers are likewise also going to be equal. And so then we can subtract that same number to both sides of this equation here. And doing that, again, these two numbers are equal to each other in that second equation, and we're just subtracting the same number from both of those numbers, so the results will still be equal. And of course this cancels out nicely, so we just get L2 equals R2, as in those two numbers are the same numbers when you plug in T1 through Tc, and that means that is also a solution of the the second equation of S. Of course, we already knew it was a solution of the first equation of S because it was a solution of T. And also all of the rest of these, it's still going to work for all those as well. But the important thing that changed when you go from S to T or T to S is the second equation there. Thus, we can say that T1 through Tc is a solution of S. And so we have proved that any solution of one of the systems is also a solution of the other system, and that means they have the same solution set. All right, let's go on to example 2. We want to write and sketch a system of two equations and two variables, one with no solution, one with an infinite number of solutions, and one with exactly two solutions. So we know if we're talking about a system of two equations with two variables, you can have x1 and x2 like this. And maybe the first equation, let's look at a familiar one. Let's say we have x1 plus x2 equals 3. And we know every point on this line gives you an x1, x2 pair that's a solution of this equation. We want to have a second equation which does not have any solutions in common with this. So if the second line crosses this one anywhere, that intersection point is going to give you a solution. So we need to have something that is maybe a parallel line like this. So maybe x1 plus x2 equals 5. And yeah, you can see that the lines never intersect, so graphically there's no solution. But just thinking algebraically, whatever pair of values you plug in for x1 and x2, there's no way that x1 plus x2 can simultaneously equal 3 and 5. So that's another way to see that there's no solution. For part B, we want to get an infinite number of solutions. Maybe we can think about how to mess with the answer that we had for A. So we want to make it so they intersect at an infinite number of points. What if we just make them overlap? What if I just take this line and like slide it down here so they're actually the same line? So like your system of two equations could be x1 plus x2 equals 3 and x1 plus x2 equals 3. That is a system of two equations, but it's kind of boring. Sometimes it's going to be not that obvious that they're the same. Maybe the second equation looks like 3x2 equals negative 3x1 minus 9. Or wait, that should be plus 9. There we go. Yeah. Okay. So yeah, those are the same, essentially, even though they look different. So that's an infinite number of solutions because every point on both the lines is a solution of the system. If you want to get exactly two solutions for part C, maybe let's think about how we can mess with what we already have. If we try to do this with a line, like let's think about where this line might go. I want to make it cross this other line at 2 points. And messing around with this, you can see that, I can make it cross at an infinite number of points, or 1 point, or 0 points. But you can't make two straight lines cross at 2 points. So turns out this is, a trick question. It's got to be some kind of like parabola or something. Like maybe if we have something like this. Something like x2 equals x1 minus 1 quantity squared. That should meet this at 2 points. We can't have both equations as linear equations. So this sort of shows you why any system of two linear equations with two variables has either 0 solutions, 1 solution, or an infinite number of solutions. And it's hard to see in R3 why this also works when you have linear equations that are like of the form, I don't know, x1 plus x2 minus 7, x3 equals 9, and then some other equations with x1, x2, and x3. The number of solutions is always going to be 0, 1, or infinity. And it's kind of harder to see why that is in R3 just by thinking about graphs. And it's especially hard to see why that is true thinking about graphs in like R10 or R1 million or something like that, because you can't draw a picture of it at all. But we can do some analysis with the algebra to see why it's true in general with any number of variables, with any number of equations. The number of solutions is either 0, 1, or infinity. And we have some new notation for this, some new vocabulary. We're going to say a system is consistent if it has at least one solution. So this has two solutions. So this one is consistent. 2 is at least 1. Infinity is also at least 1. And if it's not consistent, we say it is inconsistent. So this one here is an inconsistent system. And none of these have a unique solution. Say the solution is not unique because there's two of them here. Likewise with part B, there are an infinite number of solutions, so that's also not unique. So something with a unique solution would be like the example we did in example 1 that I also kind of was messing around with here. So yeah, that is Gaussian elimination. That is some new vocabulary and an example. In the next video, we'll look at example 3 and sort of a strategy for doing Gaussian elimination. I'll see you then.